Hey everybody, I just want to give you some notes on hypothesis tests on proportions. It should help us out to keep up with the classes that we are missing. So I want to start with the fact that we know that at this point, hypothesis tests have three general steps. The first thing I want to talk about though is what a hypothesis test on proportions generally means. So essentially, someone has a guess about the population proportion, which is the letter P. So we gather sample data to determine if the guess is correct or not. So that's the general idea of every hypothesis test, is that we gather sample data to attempt to see if the actual test itself is showing that the sample says that there has been an actual change between the two, the sample and the population. So here's what it looks like. Step one is always to write our hypotheses. So for a hypothesis test on proportions, we always have a null and an alternative hypothesis, which are written as HO and H1. So we have a null and we have an alternative. But because we're testing proportions, these null and alternative hypotheses now have different notation than we had for the test on means. So for proportions, we use the letter P. We say P is equal to P0, which is a number guess. Wow. And then our alternative has the same idea as it did in section 9.3. We have three options. Either P is greater than the guess, P is less than the guess, or we just think it's different from the guess. So it's greater, less, or different from. Those are our three options. Okay. And we choose one of those options to be the alternative hypothesis. The null hypothesis always says equal to. Okay. So we make, again, not being able to spell this morning is making this difficult. We make a choice for our alternative hypothesis, but our null hypothesis always says that the guess is correct. Our attempt is to show that the alternative hypothesis is true. That's always the goal. So how do we do that? Step two. In this case, we're going to go to our calculator, and because this is proportions, we're going to run a one prop z-test on the sample data. So what that means is that we need to think about our input. We don't need an A and a B. There's only one type of input. And we need to think about what comes out of the calculator, the output. And then we can decipher what that all means. So when we run a one prop z-test on the sample data, our input always looks like the X, which is the number of successes. Oh, I'm sorry. Hello. Our input has to include the guess. I'm so sorry, guys. The very first thing that we have to put in is the guess. Then we can put in X, which is the number of successes. And then we can put in N, which is always our sample size. And the last thing we tell the calculator is which direction our alternative hypothesis is going in. Is it greater, is it less, or is it not equal to? And we allow the calculator to interpret those results, or excuse me, to give us the results so that we can interpret them. So if you guys remember from 9.3, there's two things that have to come out of the test. The test statistic, so in this case, a z-score, and a p-value. And in section 9.1, we're going to go into more depth on what the p-value is. But the p-value definition will be really discussed in section 9.1. Okay. What we do is we use that z-score and that p-value to make a conclusion. So I can draw you a little picture of what this might look like, right? So we put the p0 guess in the middle, right? And then we put the sample, let's say we think our guess is greater. So we put our sample statistic on one end, and the p-value is actually the area that is more extreme than the sample statistic, assuming that the null hypothesis was true. So it's this little shaded area, and the smaller that little area is, the more likely that those results are extreme from our sample and would actually show that something has changed among our sample data. So let's go to step 3 so we can make that conclusion. So we've just run our test and we have our p-value. So step 3 is always to make a conclusion. And since this is just the second time we've done this, this means we're going to compare our p-value to the given significance level. So we have two choices here. Either the p-value is smaller, than we haven't done the notation yet, than the significance level, or in B, the p-value is greater than or equal to the significance level. So in option A, when we have a small p-value, that if you could, since you can still see the picture above, the small p-value implies that the sample data is very different from the guess that we were given. And that's a good thing. That will show that something has changed. So in this case, we would actually reject the null hypothesis, and we would claim that HO is true. And H1, wow, H1 is true. We would have to put that into words. So we would have to say, like, there is evidence that the proportion has gone up, or there is evidence that the proportion has gone down, or there is evidence that the proportion is different than the guess that we were given. Okay, so that was what rejecting the null means. But if our p-value is really large, then that implies that guess is actually really close to the sample, and that says that there is really no change between the two. And in this case, I know the language throws people off, but we fail to reject the null, and we claim that there's no evidence to show H1 is true. So my favorite part about the hypothesis test is that we're never actually admitting that we are wrong. We are always saying that we are just lacking the evidence to say that we were correct the whole time. Okay. And then there's one other thing we have to think about, and it is checking our conditions. So we're going to write that down at the bottom of the notes, the required conditions for proportions. And so the first condition is always the same. We want a random sample, and that would be, is it a random sample? We're like asking ourselves that question. There's two other conditions that are a little bit trickier. So we call the second one, I call it success failure. And you want to check if there are at least 10 successes and 10 failures. So X is always the number of successes. So N minus X is going to be the number of failures. Is the sample size minus the people who said yes. That should leave all the people who said no. And we want to make sure that both of those values are in fact greater than or equal to 10. And then finally, we check is the population size large enough. So this is a little bit trickier. So we say, is 20 times N the minimum population size? So we really want the sample size to be big enough. That's what the success failure is checking. But we don't want it to be too large, because if the sample size is too large, then we run into some issues in terms of being able to consider that all the people in the sample are independent from one another. And we really do need that in order to be able to make these conclusions. Okay, in the next video, we're going to go over some examples that have to do with the one prop Z test. So we'll be using the calculator as well as um, the packet for the next two examples. Okay, I'll see you in those videos.